We're back with one of the biggest energy breakthroughs in human history, a stable, energy-positive fusion reaction, all done in a lab in California yesterday. The National Ignition Laboratory used an array of lasers to effectively create a miniature star, a fusion reaction at hundreds of millions of degrees. And that was very unique in that it was not just controlled and stable, but for the very first time, energy positive. It created more energy in the reaction than the system used to trigger the reaction. Now, while the system is a breakthrough in nuclear research, there are still very serious challenges ahead when it comes down to turning it into usable electricity or energy of any sort. And to help break this down, with us is Dr. Naama Charit Yaari, a physicist with the Weizmann Institute of Science. Thank you very much for joining us. Let's start with the big question. How big of a deal is this?
Well, it is a big deal because for the first time we have a net gain in energy, and it's been a dream for nearly 70 years. So it is a big deal, but it's one step in our trial to conquer the energy problem and to have clean, very efficient energy from fusion.
Now, one of the big questions I have is, frankly, on the physics side of things. How do you contain a fusion reaction in the millions of degrees? You can't contain that with physical materials. Magnetic fields are going to be using at least as much energy as the reaction is putting out. How do you go energy positive?
So there are two ways to actually create a fusion in the lab, two ways that scientists are working on in the years that have passed. So one is using magnetic fields, like you said, and one of the, well, not one, the biggest experiment ever is being designed and built for the past nearly, I think, 15 years in the south of France. And it's an international effort. And it will be, and there they will try and achieve a breakthrough in fusion using magnetic fields. But what Lawrence Livermore actually achieved this past weeks is the other way of achieving, of making a sun in the lab, of doing fusion in the lab, and it's bombarding a very small capsule with very powerful lasers. And this path has also been carried on for tens of years now, but not with achieving a gain. So they have been advancing, and in February, the laboratory in Oxford made another huge step in the direction. But for the first time, we see a 50% gain in the energy that was put into the process. So it is a big deal. It's still, I have to say, we're not near making this energy into electricity. For that, we will need to be more efficient. We will need to make probably more than 100 times the amount of energy that we put in. But we are on the right path, and I believe we will get there with time.
That was actually one of the other major challenges I wanted to bring up, because once you created the reaction, how do you harness that energy as electricity? You're still going to be losing energy at each stage of the conversion.
That is true. And what is more even is that until now, when the experiment was taking place, they have been managing to keep the process for fractions of seconds, which is not enough if you want to make energy into electricity. So one of the big challenges is also containing and keeping a controlled reaction that will last for more than fractions of seconds, so that we could really keep it going and use it to have, eventually to harness the energy to use to heat water, let's say, and create steam and make a turbine of electricity, use it for electricity. So this is the future. It's not here yet, but that's the challenge: keeping this reaction stable and controlled for longer than fractions of seconds.
Now, we spent the past 4.5 minutes or so talking about why it's so difficult and the challenges ahead, but we haven't really gone into the raw potential of nuclear fusion as an energy source. What does this breakthrough, and really, what does perfecting this breakthrough mean for the future of human energy generation?
So today, 90% of our electricity is achieved using the burning of fossil fuels. Now, this is a resource that has a limit. It's not limitless. We have a limit to it on this earth. This is one problem. I think even the maybe worse than this is the fact that burning of fossil fuels is contaminating and is very bad for our atmosphere, for our environment. Global warming is a real issue today. And so imagine an energy that will be clean, that will solve both of we'll use water for energy. We have limitless amount of water and hydrogen on Earth. So we will make energy using a limitless resource. And we will do it without contaminating our atmosphere and our environment. Almost not contaminating it at all. It's really clean energy. So and done in a very efficient way. So if we talk today about green energy and using, let's say, solar power or hydropower, it's not enough. We can't make electricity to make our world go. We have to maybe use it as a supplement, but it can't solve our global energy issues. Fusion can, and I believe it will.
Dr. Yari, I want to get a little personal now. I understand that your father's research was critical in laying the path to success for this experiment. Tell us about that.
Well, he was one of the very first physicists to make the transition from nuclear physics into plasma physics. He worked in Rochester, New York. So actually, when I was 11, we moved to Rochester, New York, to work on what was then the largest laser in the world. And actually, when he came, he wasn't sure what he was going to do. His colleagues told me that he kind of disappeared into the basement where he set up his lab because he didn't really have a research question that he was very strong about. He knew that it would have to do a bit with fusion and lasers, but he wasn't really sure what. And they said very colorfully that when he came up a year later, he had this technology he designed so that he could measure the intensity of the laser, because we were using such high-powered lasers, it was a real issue of how we measure the energy we put in. Every instrument they used would burn and would not hold on, and they weren't able to really measure the intensity of the beams used. So his was the very first instrument to be able to measure the beam. And eventually today, this technology is used in measuring laser beams, such as the ones used in Lawrence Livermore, and in the official statement of the laboratory, of the Lawrence Livermore Laboratory, the laboratory for laser energetics in Rochester, New York, is mentioned to be, of course, the one they cooperated with. So for me, it is very moving, very exciting, because it was actually a topic at the dinner table, believe it or not, when I was 11. So
that's a very impressive set of dinner table conversations. We only have a couple of seconds left, really. But I've been hearing since 1995 that we're only 5 years away from nuclear fusion. I guess the question is it real this time?
I think it's real, but I think I can't, I'm not sure I would say even 5 years. I think maybe a bit longer, but it's a very huge step in the right direction. And, with science, we never know how long it will take, but for sure it will advance humanity. That I don't doubt.
Thank you very much. Your input on this very exciting story.